A linear problem consists of objective function and some, let's say, a specific constraint. So first of all, if we want to define our linear problem, we need to define our objective function. And this is mainly is coming based on the design of the problem or case study that we are considering. For example, if you are considering the minimum of the cost is important for us, then we go for the minimization. Or if you are considering about, for example, a profit function, then we consider maximization. Therefore, here we define as objective function as z that it will be equals to here as an example minimum sigma 1 to n fi applied xi. In some sources also we can see the notation of C here instead of F, but here I consider F to be, let's say, as same as the Matlab coding that I will teach you in the following slides. Therefore, this objective function can be defined as F transpose X, that is subject to three types of the constraint. The first type of the constraint that we call them non-equality constraint can be in sigma I a with the index of 1i xi that we can extract them as a 1 1 x1 plus a 1 2 x2, and it is going to a 1n xn that should be less than or equals b1. And again, we can generalize this as AK transpose X less than or equals BK. And finally, we will have, let's say, A KN and XN1 equals or less than BK1. The second type of the constraint, if we are considering it, it would be equality constraint that we define them as AEQX equals BEQ. And the third one, it is coming from the non-negativity that it is going xi greater than 0 or equals than 0. This would be based on the all members of the I. Therefore, also we can define a lower band and upper band for xi that considering like lower band it is going to 0 and upper band it is going to infinity. We need also to consider that x is a vector of decision variables, and F, B, B, EQ, lower band LB and upper band UB are constant vectors, and A and EQ will be considered as constant matrices. In Matlab also, we will define, let's say, a transpose with, let's say, like F prime or F transpose that you will get familiar through the coding also with that, and then the final, let's say, important thing that we should consider that for solving a linear problem, or let's say in linear programming, we will use linprog function that we will see how practically in software also we are using such function to solve a linear problem. So let's look at one LP example here. So if you consider here as let's say LP example, we have our objective function that is subject to different types of the constraints. Here in this step, we need to let's say transform these model that we have to the, let's say, the linear model to the matrix notation. So as it can be seen, we start from the objective function that it is the minimization. Therefore, we extract all, let's say, coefficient of the variables that we have as one matrix, and then the other matrix, it will shows us which variables that we are considering in our objective function. So simply, it can be seen that we have the coefficient of x1 as a minus 5, and then the coefficient of the x2 as minus 4, and the coefficient of x3 as minus 6. So here we will write them in the, let's say, matrix notation. And as I explained, also the coefficients of the variables would be considered as F transpose. And then the variables that we are considering here, we have three variables, that's x1, x2, and x3 that we will consider them. For also constraint, again, we will consider based on each type of the constraint that if it is going for the, let's say, non-equality constraint, therefore we will extract them as a matrix notation, as it can be seen that the first, let's say, three rows of the constraint, it can be considered as non-equality constraint. Therefore, the one matrix we will call it as A, that it is showing the coefficient of the variables from the left side of the constraint, and then we will have our variables as x, and then on the right side also that we are defining b, that it is showing us the matrix notation for the right side of the constraint. And finally, we will have non-negativity constraint, that it is showing us that all these variables should be positive. Therefore, here we can define based on the lower bands that how the lower bands for each of those variables is considering as zero. So then matrix notation also would be like this. And of course, we can also define this as a zeros function, that it includes n rows and then also one column. Now we want to use MATLAB software that to see how we can solve the defined problems. Before starting coding, I recommend you that first go through doclin proc here in the command. You can use it to see that how it is the, let's say, MATLAB file help here, that we are seeing that we can use different types of the linproc function that we are considering for providing solution for LP. So uh, we go through the third option, that it is x equals to linproc. It depends on how much information we have based on the defined problem. For example, here we consider the first one, it is f, as I explained, the coefficient of the x variables in objective function. And if we have, let's say, non-equality constraint, then we will have a and b. If we have equality constraint, then we will have aeq, beq, and finally for, let's say, non-negativity constraint, we will have lower band or upper band. So considering this function, we start to do our coding. I recommend you always, first of all, start your coding by CLC. This, let's say, command help us to clear all the text from the command window. And then also I recommend to use clear command, that this command also help us to remove all variables from the current work space. So somehow it's releasing them from system memory. And finally, close all. It's also a good command. If you have any open figures or something, then it will be totally closed. So starting our coding for our linear programming, first we had matrix notation that we call it as F. So here I define it the same also. I try to provide all the information that we discussed already in previous slide here, that the matrix of F that includes like -5, -4, and -6. So we can consider like this and little, let's say, tidy it up. And then the next one, it is coming from the left side of the constraint that we were discussing, that we call it as A matrix. Therefore, we provide also the information regarding that. I try to type here also 4, and the last row was 3, 2, and 0. So Here we provided also our A matrix, and then we need the right side of the let's say equality non-equality constraint. Therefore, I defined as B. Then we will have like 20, 42, and 30. So as we didn't have any equality constraint, then we do not need to add anything here. And regarding our non-negativity constraint, we had lower band only. So lower band will be defined. We can define as a matrix, or as I told you, as a zeros function. Also, it will be much easier. And here that we can consider 3 rows and one column that it is constant. All members of this let's say matrix is 0. And finally, coming to the function that already we discussed, it's coming for x and then z. And we consider also for this one lin prog for f, a, b. Because we don't have any equality constraint, then I consider them empty here. And also for the BEQ empty, and finally we have only log. So this would be also our linprog function that we provided. So we can run this by F5, or here on the tab we can run the model to see what would be the result. It's showing in the right side of workspace that, as it can be seen here, the value for the Z it is minus 78. And based on our, let's say, purpose that we, if we want to see, for example, what is the value for x, like x1, x2, or x3. So here we will see that x1 is 0, x2 is 15, and x3 can be with the value of 3. Or if you want to see the left side of our constraint, that how it would be, then we can also see the value of those. Or if we want to test our model, for example, considering like a applied x should be let's say less than or equals b. Is it correct? Yeah, it is all 1, so it is correct. And also the x variables also we can test that are they greater or equals to lower band or not. So we will see, yeah, it is also correct. So this was simply to see like a very basic example from the linear problem, how we can solve it by linear programming by using Matlab software.